Welcome to Mrs. Lee's Chemistry Academy. Today we're going to focus on intermolecular force of attraction. Tying back to the learning objective from College Board 2.1.11, that the student can explain the trends in properties and or predict properties of samples consisting of particles with no permanent dipole on the basis of London dispersion forces. That the student can describe the relationships between the structural features of polar molecules and the forces of attraction between the particles. That the student can identify the non-covalent interactions within and between large molecules and or connect the shape and function of the large molecules to the presence and magnitude of these interactions. Now, what makes a matter being solid or liquid or gas? That depends on the strength of intermolecular forces between the neighboring molecules. Solids are closely packed together, vibrating in place. With liquid molecules, they collide and slide past each other and take the shape of the container. Gas molecules are very far apart. They move around randomly and collide with one another. There are 4 types of intermolecular force that we're going to cover today. The London dispersion force, the Dipole-Dipole force, hydrogen bonding, and ion-dipole interaction. The strength of intermolecular forces depends on structure, polarity, and size of molecules, and it is directly related to the properties and behavior of a large collection of particles. First, we start off with London dispersion forces. They exist between all atoms and molecules, but predominantly in nonpolar molecules such as diatomic molecules, noble gases, and hydrocarbons. They are often the strongest net intermolecular force between large molecules. It is a temporary, instantaneous dipole created by the uneven distribution of electrons around the nucleus of an atom. It arises from Coulombic interactions of temporary dipoles, and it increases with contact areas between molecules and with increasing polarizability of the molecules, which means the ease to move the electrons. Here's a diagram showing the LDF between helium atoms. Now, as the oscillating electrons shift to the left side of a helium atom, a temporary instantaneous dipole is created, making the electron-rich end of the partially negative and the other end being partially positive. And that induces the electrons of a neighboring helium atom to shift to the left side, therefore forming a weak kind of attraction called London dispersion force between adjacent helium atoms, as you can see represented by the dotted line between the relatively positive end of one helium atom and the relatively negative end of another helium atom. Now here's a diagram showing the plot of boiling point versus molar mass for the first 5 members in the alkane series: the methane, the ethane, the propane, the butane, and pentane. And you can see there's a linear relationship that as molar mass increases, boiling point also increases. Now here is another table recapitulating the information in terms of molar mass and boiling points from methane to pentane. Molar mass goes from 16, increases to 72 grams per mole, and boiling point increases from negative 161.5 to 36.1 degrees C. As molar mass increases, the number of electrons also increases. The ease at which the electron cloud can be distorted, meaning polarizability, to give rise to temporary dipole also increases. Polarizability is also enhanced by pi bonding. Now the greater is the LDF, the greater is the amount of heat needed to overcome the intermolecular force to change liquid into gas molecules. Therefore, the higher the boiling points. Here's practice problem number 1. Explain why at room temperature the fluorine and chlorine are gases, Bromine's a liquid and iodine's a solid. Now here's a diagram showing the relative sizes of the electron cloud of these molecules and the distance between the two atomic nucleus being 143, 199, 228, and 266 picometers. The magnitude of the LDF depends on how polarizable or easily moved the electrons are when induced by instantaneous dipole. Now, iodine has the largest electron cloud, and therefore it polarizes most easily to form the greatest LDF that will pull the iodine molecules closest together to form a solid. Bromine has a smaller electron cloud and a weaker LDF, and therefore bromine molecules are relatively further apart from each other to form a liquid. Chlorine and fluorine have even smaller electron clouds and weakest LDF, making them really far apart to form gases at room temperature. The London dispersion force increases with contact areas. So here are three molecules, the normal pentane, the 2-methylbutane, and the 2,2-dimethylpropane, with their relative boiling points as 36.1, 27.9, and 9.5 degrees C respectively. Now here is a diagram showing their molecular structure. As you know, in the normal pentane, it is a long and skinny structure with large contact areas for interactions. Therefore, it would exhibit the strongest LDF, creating the closest packing and the highest boiling point. Now in 2-methylbutane, you can see there's a methyl group as a branch sticking out from carbon number 2. Therefore, interactions are less effective, and therefore it would have the medium boiling point. Now, when we go to the 2,2-dimethylpropane, it has a globular structure with small contact areas for interaction. Therefore, it would have the weakest LDF and the lowest boiling point. The second kind of intermolecular force is called Dipole-Dipole Force. It exists in all polar molecules. Now, this is not a temporary dipole, but a permanent dipole, which means it has a positive and negative ends interacting with another polar molecule by Coulombic attractions. Dipole-dipole attractions are weaker than ionic or covalent bonds. Typically, it is greater than between nonpolar molecules that exhibit LDF, because in polar molecules you have the dipole-dipole forces plus LDF. Polar molecules have higher melting point and boiling points, therefore, than the nonpolar molecules. Now here's a diagram of dipole-dipole forces, and you can see that the red line represents the force of attraction between positive and negative ends of adjacent molecules, and the green line representing the repulsive forces between light charges on adjacent molecules. And this is an example of hydrogen chloride. And the attractive forces are maximized and the repulsive forces are minimized. The dipole-induced dipole interaction is a weak attraction that arises when a polar molecule induces a dipole in an atom or in a nonpolar molecule by disturbing the electron arrangements. And if you look at this diagram here, iodine is nonpolar, however, it's slightly soluble in water because iodine has a large electron cloud, which makes it very polarizable. Now, water is a very polar molecule, therefore, it can induce a dipole interaction with a nonpolar iodine, making it slightly soluble in water. The third kind of intermolecular force is hydrogen bonding. It is a relatively strong type of intermolecular force even in small molecules. They exist when a hydrogen atom is covalently bonded to a highly electronegative atom such as N, O, or F, and it is attracted to A, the negative end of a dipole formed by N, O, and F in a different molecule, or B, in a different part of the same molecule. So here's a diagram. As you see, to the far left-hand side, we have water forming hydrogen bonding with methanol, and the O atom is attracted to the H atom. And in the middle diagram, we have ammonia forming hydrogen bonding with another ammonia molecule, and the hydrogen bond is formed between N and the H atoms. And then in the last one on the right-hand side, we have hydrogen fluoride, forming hydrogen bonding with ethanoic acid. The F atom is weakly attracted to the H atom in the ethanoic acid, and these are hydrogen bondings. When we compare covalent bond versus hydrogen bond, we need to look at two kinds of interactions. One is when water is electrolyzed to form hydrogen and oxygen gas. This is a chemical change involving breaking of covalent bonds and forming new bonds. However, when liquid water is evaporated to form water vapor, the process is a physical change involving the use of heat to overcome hydrogen bonding between neighboring molecules and to increase the distance between them. So remember, the electrolysis of water is a chemical change involving bond breaking the covalent bonds, whereas the evaporation of water is a physical change involving overcoming hydrogen bonding. Students often are confused by these two concepts, and it is really important that we make them very clear. Now, the length of an OH covalent bond in water molecule is 96 picometer, whereas the average distance between water molecules in hydrogen bonding is about 300 picometers. So you can see this covalent bond is much stronger and shorter than hydrogen bond. Now let's look at this diagram here and see how hydrogen bonding can affect the boiling point of covalent hydrides in groups 5 and 6 and 7A. The red line here represents group 6, and you can see water stands up like a sore thumb. Although it is the smallest molecule in that group, it has hydrogen bonding, whereas the others don't. Now the blue line representing group 5A, and that represents the hydrogen bonded with the ammonia and phosphorus. And you can see that ammonia stands up like a sore thumb in the boiling point again due to hydrogen bonding, although it is the smallest molecule in that group. And the green line representing group 7A, again, hydrogen fluoride stands up like a sore thumb with the highest boiling point in that group, although it is smallest in size. However, with group 4A, you can see the methane follows that normal trend of decreasing boiling point, and it is smallest molecule in that family group, but it doesn't have hydrogen bonding, and that accounts for why it would have a low boiling point. Now, there's hydrogen bonding in DNA. The thousands of individual units of nucleotides in DNA that make protein contain one of the 4 bases: adenine, thymine, cytosine, and guanine, A, T, C, and G. Each base forms specific hydrogen bonding with the complementary base, that is A with C and C, A with T and C with G. So you can see in the following diagram that the O atom on thymine is forming hydrogen bonding with the H atom in adenine, and the H atom from thymine is forming hydrogen bonding with the N atom in adenine. When DNA replicates, the hydrogen bonds that join the base pairs between the O strands are broken, and new complementary bases are added by hydrogen bonding to the original strand, resulting in 2 identical copies of the original DNA. And here's a diagram of how new strands are formed, passing the hereditary material from the parent to the offspring. There's IMF between substrate and enzymes. Enzymes are large protein molecules with complex structures that act as biological catalysts to increase rate of biochemical reactions by lowering the activation energy. A substrate, that means the reactant, binds to the active site of enzyme with specific properties and shapes through intermolecular forces such as hydrogen bonding and dispersion forces. And in everyday life we say like a key fitting into a lock. After the reaction occurs, the products are then released from the active site. So to summarize what we have learned today, students have learned how solids, liquids, and gases are formed based on relative strength of intermolecular forces. In other words, how far molecules are apart from each other. We learned how to explain linear dispersion forces using particulate drawing, and how the strength is related to properties such as boiling point of alkanes and why halogens are solid, liquid, or gas. We learned how to explain the dipole-dipole force and dipole-induced dipole interaction using particulate drawings. And finally, we explained the formation of hydrogen bonding and its effect on boiling point, the function in DNA replication, and large biological molecules. From the team of MLCA, we would like to thank you for watching our video, and we hope to see you again next time.